Hello everyone, I'm Paul and today we're solving problem 3443, maximum Manhattan distance after k changes. This is medium and there are at least two ways to solve this one, so here I will show you both. We're given a string s and an integer k. String s consists of the characters n, s, e, w, which correspond to north, south, east, west, and integer k represents the amount of characters that we can change in the string. We are initially at the origin. We can change at most k characters to any of the four directions, and our job is to return the maximum Manhattan distance from the origin that we can achieve at any time while performing the movements in order. Now, in case you don't know, Manhattan distance between 2 points is the absolute distance between the points. So one of these points will be the source. Let's say we have this. We start from the source and let's say we move one step up and one step to the left. Now we're here. So in this example, the Manhattan distance from here up to here will be 1, 2. Now let's say we have this string and k is 1. In these problems I recommend you to draw this, it might be helpful. And initially we are at the source, we are here. Now let's say we are not using k and we are moving in these directions. First we move from the source one step to the north, so now the Manhattan distance is 1. Next we move one step to the west, meaning to the left, so now we're here and the distance from the source is 2. Next we move one step to the south, meaning we move here, and the Manhattan distance from the source to this point is 1. And next we move one step to the east, so now we are back in the source. Now the Manhattan distance from the source is 0. Now we have some important information here. When we move one step to the north, we are one step away from the source. But then we moved one step to the south and we were 2 steps away from the source, and when we moved south, next we were one step away from the source. So what we can see here is that north and south obviously are opposite forces. West and east are also opposite forces. And now remember we have 1k here, so now let's see what happens if we use this k. We start from the source and we move one step to the north. Now we are here and the Manhattan distance is 1 up to this point. Next we move one step to the west, so now we are here, Manhattan distance is 2. Next we have south, but we have a north here, so maybe we should use our k here. So now we have 0 k's and we can transform this into north, and now we can move one step to the north. So from here we move here. And now Manhattan distance is 3. And finally we need to move to the east. We don't have any more k's, meaning we can't change this. We know here we have a west, but we can't change this in this case. So we move one step to the east, meaning we move here, and now Manhattan distance from the source is 2 again. And the maximum value among these distances is 3, so this is the result. Now there are at least 2 ways to solve this, and I will show you both. So let's go with the first approach. Now let's say we have the same input and we will have 2 variables here, latitude and longitude. Remember that this and this are opposite forces, and this and this are also opposite forces. So whenever we find an n, we will add 1 to latitude here. Whenever we find an s, we'll subtract 1 from latitude. Whenever we find an e, we'll add 1 to longitude, and whenever we find the W, we'll subtract 1 from longitude. And by doing this, we can take the absolute value of each of these and add these values, and this is how can we get the Manhattan distance at each step, because we are iterating this from left to right with an I pointer. So first we start here from index 0. We have an n. This means that we need to add 1 to latitude, so this is now 1. Now our current Manhattan distance is the absolute value here, meaning 1, plus the absolute value here, meaning 0. So our current Manhattan distance is 1. And this happens to be our biggest Manhattan distance up to this point, meaning the result is currently 1. And here we want to check if we can make our Manhattan distance greater, because we have 1k here that we can use. And maybe we have to use this now. But remember, our Manhattan distance is currently 1, and we have seen one element only. So given that we have seen one element and our Manhattan distance is also 1, we can't use any case here. I mean, we have the maximum possible Manhattan distance. It doesn't make sense to use a k here. Next we have a w, meaning we need to subtract 1 from longitude. So this is now -1. And the current Manhattan distance is the absolute latitude plus the absolute longitude, meaning 1 plus 1. So this is 2. And up to this point we have seen 2 elements. Our Manhattan distance is 2, meaning we don't need to use any case here. We already have the maximum possible value up to this point. So our result will be the maximum among our current result, meaning 1, and this 2. So the result is now 2. Next we update I, we are here, and this is the key for this approach. We have a south here. So remember, first we were at the source, we moved one step to the north, so we moved here, then we moved one step to the west, meaning we moved here, and now we are moving one step to the south. Given that we are moving one step to the south, we need to subtract 1 from latitude, so this is now 0 again. Our current Manhattan distance is 0 plus 1, meaning 1. But we have already seen 3 elements, and our Manhattan distance is only 1. This means that somewhere in between, somewhere in here, we have opposite forces, and more specifically, north and south are opposite forces. This means that we can use a k here, and to use this k, we will use k times 2 units. Why? Well, because we'll use 1 unit to counter this force, meaning to go back here to counter this force. So now we move from here to here, and we will use another unit to change direction, to transform this into north. So for every k we use 2 units, one to come back here and the other to change direction. So right now we are here if we use our k, and now we are 1, 2, 3 steps away from the source, meaning the Manhattan distance is now 3. And just to be clear, what we did here is we took the current Manhattan distance plus k times 2, and this is 3. And 3 is greater than our result, so now the result is 3. And here we did a simulation for using this k at this point, but maybe we need to use this k somewhere in the future, because remember, we need to find the maximum Manhattan distance at any point. So now we update I, and we have our k again, meaning we have this again. So we have an E, meaning we need to add 1 to longitude, so this is now 0. And now our Manhattan distance is 0, meaning 0 plus 0. So our distance is 0, but we have already seen 4 elements. This means we have opposite forces here. This means we can use this k here. So remember, we moved one step to the east, meaning we moved from here to the source again. So we need to counter this, meaning we move one step to the left, we are here again, and now we need to change direction, meaning move another step to the left. We move here, and this is how we can use this k. So our current Manhattan distance, which is 0, meaning we are here, plus 2 times k is 2. This means if we use our k here, our current Manhattan distance would be 2. And the maximum between what we have in the result and these 2 is our result. So we keep our free and we keep going. So finally we reach the end, and this is our maximum Manhattan distance at any point. So we return this. So just to be clear, we iterated this from left to right, and at each point we took the Manhattan distance and we tried to use our case, if necessary, to get the maximum value at each point, and this is how we reach our maximum value, which in this case is 3. So at this point we took the Manhattan distance and we tried to use k. At this point we took the Manhattan distance and we tried to use k, and so on. This is what we do at every point. So this is it for the approach. Time complexity for this will be roughly big O of n, and space complexity will be big O of 1. So now let's go with the code, and remember that next I will show you another solution. First, the result, latitude and longitude are all 0. So result, latitude, longitude equals 0, 0, 0. And now we'll use enumerate in Python. So for every index and character in enumerate s, if the character is n, latitude plus equal 1, else if the character is s, latitude minus equal 1, else if the character is east, longitude plus equal 1, else longitude minus equal 1. And now this is the key for this problem. First we'll take the Manhattan distance, we'll call this m, and this is absolute latitude plus absolute longitude. And now if the Manhattan distance plus k times 2 is smaller than I plus 1, meaning if we can use all the k's and not exceed the current amount of elements, the result equals the maximum among the result and Manhattan distance plus k times 2. Else, meaning if I take in the current Manhattan distance plus all the k's times 2, we exceed the current amount of elements, well, in this case the result will be the maximum among the result and the current amount of elements, meaning I plus 1. Okay, because think about this. If by taking all the k's we exceed the current amount of elements, well, we need to take less k's. And more specifically, we need to take just enough k's for the current amount of elements, meaning I plus 1. And finally, we return the result. So this is it for the code. Now let's submit this and see if it works. Here I have an extra column, so let's fix this and try again. And as you can see, this works. So now let's go with the second approach. Now let's say we have this same example, and for this approach, we'll try to reduce this from 2 pairs of opposite forces to 1 pair of opposite forces. Let's see what I mean here. Here in this space, we can move to the north and the west. Here, we can move to the north and the east. Here, we would be moving to the south and the east. Here, we will be moving to the south and to the west. And by doing this, now we have only 1 pair of opposite forces here. This is one way to work with this. And here we have another way to work with this. So now we can try each of these forces and see in which one do we get our maximum Manhattan distance. And the way to do this will be the following. Let's say we start here at NW. Whenever we find an N or a W here in the string, we add 1 to the count. And whenever we find the opposite force, meaning S or E, we subtract 1 from the count. Okay, so we will only care about this in this case. We start here at NW and we only care about this. So the count is initially 0, and now we iterate this from left to right. The I pointer is here, we have an N. N is here, and remember, when we have an N or a W, we add 1 to the count. So now the count is 1, we update I. Now we have a W, and the W is here, meaning we add another 1 to the count, so now the count is 2. And now this is the key for this approach. We have a south, and the south is here, meaning we need to subtract 1 from the count. But we have 1k, and we don't care about this anymore. We only care about this and this, so we can use this k right now. So we use this is now 0, and we transform this into north, and now we can add 1 to the count because north is here, so now the count is 3. And 3 happens to be the maximum value that we have seen so far, so the result is now 3. First we saw a 1, so this was initially 0, and then this was 1, and then we saw a 2, so this was 2, and then now we saw a 3, so this is now 3. Remember, we are trying to get the maximum value. Now the I pointer is here at E, and this means we need to subtract 1 from the count. So now the count is 2. And 2 is smaller than our current result, which is 3. So we keep this 3 and we continue. Next we update I and we reach the end. And now we have already tried this direction. So we need to repeat this same process with this, and these directions. Now we take this as the candidate, and the opposite of this force is this force. Okay, so we only care about this. We don't care about this, and we don't care about this. The result is initially the maximum value we got here, meaning 3. And we iterate this from left to right. From index 0, we have an N. Whenever we have N or E, we add 1 to the count, so now the count is 1. Now the I pointer is here at W, meaning we need to subtract 1 from the count, but we have 1k. And we have only 2 forces, so the best possible time to spend this k is right now. So we use this is now 0, and we transform this W into an E. So now we can add 1 to the count, this is now 2, and the maximum between 2 and 3 is 3, so we keep our 3. Now we have a south, south is here, meaning we need to subtract 1 from here, so this is now 1, 1 is smaller than 3, so we keep 3. Finally we have an E, E is here, meaning we need to add 1 to the count, so this is now 2, and 2 is smaller than 3, so we keep 3. Now we update I, we reach the end, and now we have already tried this and this. we need to try this and this. So let's go with this one. Remember, we are iterating this from left to right, and now this is our candidate. So first we have an n is here, and now we need to subtract 1 from the count, because remember, now our candidate is this, and we have 1k, so we can use this k right now. Now we have 0k's, and we transform this into south, meaning we can add 1 to the count. So now the count is 1 is smaller than 3, so we continue. Next we have a w, meaning we can add 1 to the count, so this is now 2 is still smaller than 3, so we keep 3. Next we have an s is here, so we can add 1 to the count, this is now 3 equals our result, so we continue. Finally we have an e, so we need to subtract 1 from the count, this is 2, and we keep our maximum result, which is 3. Now we need to do the same with this candidate. We start here, we have an n, meaning we should subtract 1 from the count, but we have 1k, so we use this, now we have 0k's, and this is now south, so we add 1 to the count, this is now 1, and we keep our 3. Next we have a w, we don't have any more k's, so we need to subtract 1 from the count, this is now 0. Now we have a south, and south is here, so we can add 1 to the count. Next we have an east, and east is here, so we can add 1 to the count. So finally we keep our 3. Now we have already tried our 4 directions, the 4 candidates, so we return the maximum value, which is 3. Time and space complexity for this will be roughly big O of n, and space complexity will be big O of 1. So now let's go with the code, and hopefully you will get the idea. The result is initially 0, and we will return this result. And here in between, for every direction in and W and E, SW, SE, we'll copy K, we'll call this KK. Distance is initially 0, and for every character in the string, if the current character is in the current direction or we have k's remaining, we can add 1 to the distance, and if not c in direction, we subtract 1 from our case. Else, meaning if we don't have the current character in the current direction and we don't have any more case, in this case we can subtract 1 from the distance, and each time we need to update the result with the maximum among the result and the distance. So this is it for the code. Now let's submit this and see if it works. As you can see, this also works. It has the same time and space complexity. So if you found this video useful, please drop a like, subscribe, and see you in the next one. Bye bye.